Alright, so in this particular video, I will show you how to do a few multiple choice questions regarding forces just for the entire unit in general, so it'll kind of be randomized, okay? So the first one in this video is that you're given this particular diagram. The tension on the left string is called T naught. The tension on the right string is given as 40 newtons. The angle touching the ceiling here is 30, and on the right side is 60. And it wants us to find the tension T naught on the left string. Okay, so here's T naught. Now, I do want to point out that this particular question can be very easy if you know a few facts. Fact number one, the angle that is steeper relative to the horizontal axis will always produce more tension. That's important because this is a multiple choice question, so it's important to use the deduction skill. The right string here is given as 40 newtons. The magnitude here is 40 newtons. But if you look at this diagram, this is 60 degrees versus 30 degrees. The angle that is steeper relative to the horizontal axis will always generate more tension. So the fact that this is 40 newtons tells you that T naught has to be less than 40. Okay, so when the angle is smaller, the tension is not as great. So this is 40, so therefore right away I know T naught cannot be greater than 40 or 40. So what I'm going to do is I'm going to do deduction. I'm just going to cross out 40. T naught, because the angle is less, cannot be the same value. It has to be something smaller than 40 for this particular problem. I'm also going to cross out 52. Well, if it can't be 40, it can be 52. I'm also going to cross out 69. Okay. Now, well, you're left with then choice A and C, right? It's either 20 or 23. Well, all we have to do is just use a little common sense. Find Tx, because the system here is in static equilibrium, nothing's moving. So the horizontal components on each side, Tx to the right here must equal to T naught x to the left side. Well, how do you find this component? Well, it would just be the hypotenuse times cosine of 60. The angle that my cursor is tracing out here, the angle is going back and forth here is also 60 because this is 60, which is touching the x-axis. This angle that I'm tracing back and forth with my cursor is also 60 because it's touching the horizontal axis. Okay, so by that you can just do 40 cosine of 60. All right, it's cosine because this is the adjacent to the angle 60. Well, to find this horizontal component, you just multiply the hypotenuse by cosine of 60. That gives you 20. Well, if the x direction isn't moving because this is a static equilibrium problem, it suggests that this particular arrow pointing left is also 20. It's just pointing leftward. Well, if this is 20, this is T naught x, you're trying to find T naught, and T naught is your quote-unquote hypotenuse. So if your adjacent is 20, the hypotenuse has to be greater than 20. So by that deduction, I can just cross out 20, right? I know T naught can't be 20 because its horizontal components are, it's already 20. So therefore, T naught has to be something greater than 20. So the only answer that makes sense is C. So I'm just going to highlight that, okay? Well, excuse me, I didn't even highlight that, but I'm just going to go with C. All right, other than that, let's move on to the next one. So in this particular problem, we have a satellite that's in line with a planet of mass m1, which is on the left side here, and then a moon of mass 2, so m2 is the moon, and it says here m1 is greater than m2, which is an important piece of information. But it says the net force on the satellite, so here's the satellite, that's a square in the center, is 0. So it's just stationary, right? Which suggests that the moon is pulling on it to the right, and then this planet is also pulling on it to the left, but with equal amount. In order for a satellite to remain stationary, the two forces must be equal in magnitude but opposite in direction, and that's important. Now the question asked is, how does the distance between the satellite and a center of planet D, of the planet D1, compare to the distance between the satellite and the center of the moon D2? So here's D1, here's D2, and you notice here it's just not drawn to scale, okay? So it wants us to kind of, make a statement, make a true statement between D1 and D2. So this one's not too bad. Well, I'm just going to set this up. Again, the satellite is being pulled towards the moon because given any two masses, there's some sort of force of attraction. But at the same time, the planet will also pull the satellite, okay, towards itself. But you notice here in my work here, I drew both these vectors the same because they are equal in magnitude, opposite in direction. For an object to remain in equilibrium, your forces must equal in magnitude and opposite in direction. So planet 1, once again, is pulling the satellite to the left. the moon is pulling the satellite to the right, but it stays still. Therefore, it suggests that FG1 and FG2 here, I'm just going to call it 1 for planet 1 and then G2 for the moon. The two magnitude must equal, the two forces must equal in magnitude, okay? So here, f of g1 must equal to f of g2. Well, the function for f of g for these types of problems, based on the schematic that we're given here, is going to be Newton's gravitational constant times the mass of the planet, which is right here, acting on the satellite, right? So there's the planet pulling the satellite to the left, divided by the distance from center to center square. And likewise, f of g2 will involve the satellite and the mass of the moon, which is m2. So I'm just going to write this function twice, but you notice that the only difference here on the left side is the mass of the planet. On the right side is the mass of the moon, and both of these functions have the mass of the satellite in common because it's pulling the satellite. The only difference here is really the denominator, and that's ultimately what the question is asking, to kind of make a true statement regarding d1 and d2. Well, based on my work here, I can cancel out capital G on both sides because it appears on both sides. At the same time, though, m of the satellite also appears on both sides, so I can cross that out. So the only thing left here is just really this particular ratio. All right, the mass of the planet divided by the distance from satellite to planet, and then the mass of the moon relative to the satellite and the moon, the distance from the satellite and the moon. But again, we're not really asked to do any math here. We're just asked to pick one of these answers, right? Which of the following statement is correct here? Okay, so intuitively, if you think about it, it states that the mass of the planet, right, is greater than the mass of the moon. Right here in the statement, it says m1 is greater than m2. So I made this statement in green for you. This is important. m1 is greater than m2. This is useful because I'm just going to think like this. Well, m1 is large or larger, right? m2 is small or smaller. Well, how do I get it to equal? Well, if you have a large numerator and on this side you have a small numerator, well, to get it to be the same, you must on the left side divide also by a large number. Okay, and on the right side, if you have something small to start with, for it to equal, you must divide by something smaller. Okay, why? Because large divided by large reduces down to the same ratio as a small divided by a small. So for example, if you have 10 divided by 10, it's the same as saying 2 divided by 2, because 10 over 10 is 1, 2 over 2 is 1. So if you're keeping up with the analogy here, well, this is 10 and that's 2. It suggests that d1 must be greater than d2. I'm ignoring the square here because the question has nothing to do with the square. It's just saying which of the following statement is true. Okay, so by this deduction, if the mass is large, it can be a farther distance away. If the mass is small, it needs to be closer to the satellite. So by that, I'm just going to highlight choice A. Okay. All right, let's move on to the next one. In this particular problem, it says a space capsule has a mass of m0 of 500 kilograms. It's launched into a circular orbit at a height of 400 kilometers above the surface of the planet, and this is important. It says above the surface, not from the center, which has a mass of m0 of 1 times 10 to the 24th kilogram, and it has its own radius of 1 times 10 to the 6 meters, and wants us to find the orbital speed, right? So here are your options, A, B, C, D, E. So this one's not too bad. So for this particular problem, you have to recognize that the force that is keeping the satellite in orbit is the force of attraction between the satellite and the planet itself. So I'm just going to call this F of G. Okay. F of G, however, because it's keeping this particular, a capsule in orbit, it's producing a centripetal force on the capsule because the capsule is moving in an orbit. And anytime you have something revolving or orbiting in a circle, the centripetal force exists. So I can make this particular statement. Well, for this diagram, based on how the capsule is drawn here, I'm just going to draw this vector tangent to the circular path, and I'm just going to call that my tangential speed or tangential velocity, whatever you want to say. All right. But what's more important is this. Your centripetal force is your gravitational force for this particular problem, because the force of attraction between the what planet is it? Between the planet and this capsule is what's generating a centripetal force. Okay, it's keeping this particular capsule in orbit. So I can just expand F of C into mv squared over r. Well, it's important that you recognize what mass is needed here, right? An object that is in orbit will experience centripetal force? Well, using common sense, you have a planet and you have a space capsule. In this particular frame, it's the capsule that is moving. So which mass you put here is the mass of the capsule, which is denoted as m naught for this particular problem. So it's important that you know which mass to use. It's not a guessing game. Centripetal force is for the object moving. In this case, it's the capsule that's moving. So the mass on the left side in my work here must be the mass of the capsule. Okay. V here is your tangential speed. Make a note of that. V here, even though it's V, is tangential speed because your velocity keeps changing because the direction changes. Okay. All right, on the right side, I just broke up f of g. By definition, it's just capital G and the product of the two masses that are involved. Here we have the mass of the planet and also the mass of the capsule. And then on the left side, there's r. On the right side, there's also r, but it's r squared because that's the function for f of g. I do want to point out this is important though, okay? By the way, m naught cancels out. Hopefully you keep up with the work here. What's more important is this r. Make a note of this. For centripetal force, the r in this particular function is always defined as from the center to the orbit. Okay, it's important that you measure stuff correctly. The r in this f of g function is measured from center to center. And sometimes these r's are the same, but they are not always the same based on the type of system given to you, especially for like binary system. Okay, so could they be the same r? Yes. Do they always have to be the same? The answer is no. So make sure you always measure stuff correctly. All right, so I'm just going to stick with this stuff, center to orbit and then center to center. Okay, if you look at this particular diagram, here's the mass of the capsule. Here is the center of the planet. Well, what is that distance? Well, from center, which was where my cursor is right here, to where the capsule is, that is the distance of r naught. Watch my cursor. The radius of the planet is r naught, but I'm not at the orbit yet. I have to extend my cursor more, which is the extra distance of h naught. So really, what is this r? It's r naught, which is the radius of the planet in this particular diagram, plus the height above the surface. Okay, so it's measured from center to orbit. On the right side, well, from center to center. Well, if I take my cursor and put it back at the center of the diagram and go all the way to the center of this capsule, that is also the same distance, which is the distance r naught plus h naught, right? So in this particular problem, r on both sides are the same because it happens to be so. It's not always the same, so keep that in mind. So as you can see here, you have an r naught plus h naught on the left side in the denominator. On the right side though, you have an r naught plus h naught square. Well, that just tells you that there are two of them, so I can cancel out one of them. Okay, so at this point, make sure you cancel out the right quantity here. I would cancel the square. Don't cancel this r naught plus h. That's the improper way to do it. All right. So if you clean this up a little bit, the only thing left on the left side is v squared. The only thing left on the right side is just gm divided by r naught plus h naught. Well, to get v by itself, you would need the radical of both sides. So this is what I did here. I just kind of skip a step. So I just said v is equal to the square root of gm over r naught plus h naught. Okay. So at this particular junction, you have everything already. You know what g is. You know what mass is, you know what r naught is, you know what h naught is, because everything is given really here in this particular problem. All right. So g here, Newton's universal constant, is 6.67 times 10 to the negative 11. Well, what's the mass of the planet, right? The mass of the planet is given as 1 times 10 to the 24th kilogram, where I'm cursing back and forth in the statement. So that goes in the numerator. Okay, and on the bottom though, you notice here, this is where you got to be careful, right? The problem gives you the height in units of kilometers. Well, you need to convert kilometers to meters because the universal constant has the unit of meters in it. Okay, so it's important that you recognize units before you start adding stuff. So you notice here, I took 400 kilometers and I converted to meters. Well, 400 kilometers is just 400,000 meters. So if you don't know how to convert, that's a you problem. You need to learn how to convert and keep up with that part. And then once you do that, this part is super easy to do. Now, well, what's h naught? H naught is given in the problem as 1 times 10 to the 6 meters. So now I have meters and meters. I can just add both these distances up. Okay, so don't get sloppy. Make sure you pay attention to units. If it matches, add it. If it doesn't, convert before you add. So if you do all that, okay, you'll get a value of, what is this? 47642,857.14, which is a massive number. And then you got to square root that. If you square root that correctly on your calculator, you'll get 6902.38, and that matches with choice D because that is just now written in scientific notation, okay? So 6,902.38, that is closest to choice D. So I'm just going to highlight D as my answer. All right, let's do this next one. So here we have a 5 kilogram object that is released from rest near the surface of a planet, right? And it says the mass of the planet is unknown. After 2 seconds, though, the object has fallen 30 meters, and it says air resistance is negligible. And it wants us to find the magnitude of F of G acting on the 5 kilogram object near the planet's surface. All right, so how do you do this? Again, for this particular problem, you're asked to find F of G, or the magnitude F of G. So I would just start with this, right? I would start with this because the mass is given, and it says that, the object is falling, which is implying that it's accelerating, okay? So I'm just going to plug in what I know. F of G is mass times gravity. Well, I know what mass is. Mass is 5 kilogram. And you notice here I highlighted G in yellow for you because I don't know what G is, right? So based on the information, like, how do you find G? Well, if you are thinking about this particular function, then I highly encourage you to get off of it, okay? Why this particular function exists, to find the acceleration due to gravity on any given planet at the surface, you can use G, which is Newton's universal constant, times the mass of that particular planet divided by the radius of the planet. However, as you notice here, I would not use this because the mass of the planet is not given, right? So even if you have a function, know if you can use it based on the scenario presented to you. In this particular problem, I will steer away from this function because, well, it says here the mass of the planet is unknown. Well, if you don't know the mass of the planet, how are you supposed to find the acceleration due to gravity at the surface for that particular planet? So even though you can write the function out, it's no good for this particular scenario. What I'm going to do, though, is I'm actually going to use kinematics, okay? Well, why would I use kinematics? Because the problem kind of leans that way. It says after 2 seconds, which is some sort of time interval, it has fallen 30 meters, which is your vertical displacement. Well, if you have mastered your kinematics, you know that you can find acceleration based on the information given. So here I wrote out delta y is equal to VIT plus 1 half GT squared. Well, I know values. VI is 0 because it says dropped, right? Release from rest, so VI is 0. I know my vertical displacement is negative 30. Why is it negative? Because it's being dropped, so it's falling downward. So this is important. So don't get sloppy with your sign, okay? Delta y here is negative 30 because it's going below. It's being dropped. It's not being tossed up. Here, I just carry this 1 half down. G is what I don't know. Well, how much time has elapsed? 2 seconds. And 1 square that because the function, again, your displacement function calls for t to be squared. So if you simplify it, right, 2 times 2, or 2 squared is 4. 4 times a half is just 2. In case you wonder where that 2 comes from, I just simplify your work for you. All right, and then to find G, you would simply divide both sides by 2. All right, so therefore, G is just 30, or negative 30, divided by 2, and that will give you negative 15 meters per second squared. Well, once you find G, really, you're done, right? Because to find the magnitude of the force of attraction, you needed 2 quantities, the mass and acceleration due to gravity. Using kinematics, you just found G, so I'm just going to go ahead and plug it in. So 5 gets carried over, and instead of G, I'm just going to plug in G as negative 15 meters per second square. And then if you do that correctly, you'll get negative 75 newtons. But the question asks for magnitude. So the only answer that matches that is 75. So magnitude would suggest that you just ignore the sign or the direction. Okay, so that's that for that one. All right, so here's the last one of this particular set. It says here a 2 kilogram cart rolls. So here's the 2 kilogram cart on the bottom, and it rolls and it has a 1 kilogram block on top of it. Okay, it says the coefficient of static friction between the cart and the block is 0.7. Well, it says if a horizontal force of 15 newtons, which is drawn here in the diagram, acting on the cart on the bottom, is applied, and it says the block does not slide with the cart. Okay, it doesn't slide, on the cart. aka it's going to move together as one. It wants you to find the magnitude of the horizontal component of the force that acts on the block that exerts on the cart. Okay, so well, what's causing the block to go with the cart? Well, it's called static friction. The problem clearly states that it does not slide on the cart, meaning it moves together, so it sticks to the cart. Okay, so let's do it. Well, here is your force of static friction. Okay, if you put a block on top of a cart, that creates more weight is going to cause the system to accelerate slower. So in this particular case, if your view is from the cart, f of static would point leftward because it's hindering the cart's ability to move faster. However, if you put a block on top of the cart and the block moves with the cart, well, what's causing it to move is actually the same force. So, okay, so why is it the same force? It plays a different role based on your perspective. If you look at the cart, the force is static would point left, but if you look at the block, well, what's causing it to accelerate to the right with the cart? That is this force of static that's sticking to it. Okay, all right. Now, ultimately, the question is asking what is the magnitude of the horizontal component of the force that the block exerts. So here's the block. It exerts some sort of static friction on the cart, right? So we're supposed to find Fs. So let's do it. If you look at the block, now why would I look at the block? Because the question is really focusing on the block, right? Saying the horizontal component of the force that the block, right, that the block exerts. So right away, that's gonna cause me to focus my attention on the block. So here, I'm just gonna make this general statement. Net force on the block is equal to the mass of the block times the acceleration of the block. Well, what is the mass of the block? What is the force acting on the block? That would just be Fs. So the only thing causing the block to accelerate to the right with the cart is the static friction. Well, so instead of net force on the block, I'm just going to replace with the force that does exist for this problem. I enlarged it here. Fs is what is causing the block to move with the cart. So there's only one force, that is the force of static friction between the surfaces of the block and the cart. Well, what mass? Mass of the block times A. Well, here, I know the mass of the block is 1 because it's given. What I don't know is I don't know A, right? I'm trying to find Fs here, but I don't know what A is. So I can just find A, okay? Well, if you look at this particular system, it clearly states that the block and the cart are not sliding relative to each other, meaning they accelerate as one. So I can just look at the system as a whole. So therefore I can just say, well, F system is equal to Fm system times A. Well, what's the force acting on the system? It would just be 15 newtons. So even though 15 newtons acting on the cart, really I can treat this as one big block because it's moving as one, right? So you're applying a 15 Newton force, but really you're pushing both objects because they accelerate together because it said so. Well, the 3 kilogram comes from adding 2 kilograms and 3 kilograms. The A is what I don't know. So to find A is super whack, right? Super easy. Divide both sides by 3. So 15 divided by 3 is going to give you a value of 5 meters per second square. So once I know that, I can just plug it back into my work, right? The only thing I was holding back earlier was the A. So here, the mass of the block is 1. Well, how fast does it accelerate? Well, it has to accelerate at the same rate as the cart. Otherwise, they'll slide off. But the problem says that it doesn't slide off, meaning the cart and the block must have the same acceleration. So therefore, the system accelerates at 5. So therefore, the block must also accelerate at 5. So therefore, the force of static of friction acting on this particular diagram is just 5 newtons. Okay. Now, I like to point out misconceptions that you might be tempted to do. Right? Some folks might just jump to this particular statement. Right? The static friction is mu s times Fn. Well, here's f of g. Okay, here's f of n, right? Because for the block, the surface between the cart and the block, that's where you're drawing your contact force from. And then this is f of n, okay? Based on this particular diagram, well, the weight of the block is the same magnitude as the force exerted by the cart onto the block, right? To keep it stationary in the vertical direction. So we can say here, f of s is mu s, and f of n can be replaced with mg, but which f of g is this? F of g of the block, right? So again, the red arrows here are drawn touching the block. So everything is looking at the block right now. Well, you can break f of g up into m times g. Again, this m here for the mass of the block, because this is your surface, and from your surface, you just count the block that's sitting on top of that, right? Well, here, mass of the block is 1, g is just 9.8, and the coefficient of static friction is given the problem as 0.7, right? And if you do this, you get 6.86. And you might be tempted to pick C, right? But this is so wrong, right? This is so wrong, okay? Because f of static here that you just calculated, if you were tempted to do this, 6.86 is the maximum value that the block can experience, okay? Maximum value. So I made a note here for you. that F of S is called a reaction force. It can be between 0 all the way up to 6.86. However, for this particular problem, you don't need all of this 6.86. You actually only need 5. Okay, so don't always just calculate F of static based on this particular function. You have to run a test. You have to know how much you need versus how much you could generate. So once again, 6.86 Newton here is how much static friction this particular problem can generate between the surface of the cart and the block. However, you actually only need 5 newtons, okay? So make sure you know what you need versus what you could generate, okay? So therefore, 5 newtons your answer. And if you were tempted to pick C by doing this, I would say this is pretty whack, okay? All right, I hope that helps. Keep up with misconception. Hopefully you don't make it. Stay nerdy, don't be whack.